Hello, everybody. Thank you for joining us today. We are just waiting for a few more people to log on, and we'll be starting in about 2 minutes' time. Welcome, everybody. Thank you for joining us for this materials testing theory and practice webinar. I just wanted to go over a few things before we get started today. So this is a Mecmesin webinar. Mecmesin falls under the umbrella of the Physical Properties Testers Group. Some of the other companies under that same umbrella include James Hill and Aluris. If you are interested in learning more about any of these divisions, you can visit our events page and see the content and on-demand webinars they have available. We also have a technology lab located in Sterling, Virginia, and Slinfold in the United Kingdom. We established these labs as a way to support our customers through education, proof of concept, and testing demos. We know that a lot of people have changed jobs over the past year or taken on new roles and responsibilities or even expanded the types of testing that they're currently doing. So if you need any assistance with any type of physical testing, please feel free to reach out. We can get you in contact with just the right person. That being said, I wanted to introduce some people on today's call. Carl Bramley is our presenter for today, and my name is Sharon Smorenberg. I'm one of the organizers. Then we have various support staff throughout the United States, Europe, and Asia. So if you do need information or help, we have somebody that can assist in your area. And last but not least, we do want to keep things interactive, so please feel free to ask questions. Click the raise your hand icon and we can unmute you, enabling you to ask your question out loud. Alternatively, you can use the questions box and type in your question. We will read it to the group and provide you with an answer. This webinar is going to be recorded and you will get a copy of the recording to the email that you registered with. If you want to review anything for additional clarity, or if you have a colleague who is interested in attending but wasn't able to make it, please feel free to pass this recording along to them. And with that, I will hand it over to Carl.
Thanks, Sharon. Thank you for that. Good morning or good afternoon to everybody. The purpose of this this webinar is to do an introduction to materials testing. Basically, the properties of materials, what we use to test them. And there is another webinar in a couple of weeks' time, which will outline further testing methods and other equipment and software that we use for doing the testing. But first of all, we'd like to take you through a brief introduction. So we're going to be looking at an understanding of materials testing, the properties of materials, what we use to test them.
Carl, I'm sorry to interrupt you, but yeah. It seems that we can't see your slides changing at this stage.
Right, okay. I'm screen sharing at the moment.
There we go.
Can you see them now? I've just re-enabled.
Yes, I can.
It was on green, but it's in. Okay.
Thank you.
Start again. So the properties of materials, what we use to test them, results required from testing, and the grips and fixtures we use, and touching on a little bit about extensometers and extensometry. Should be able to see the next slide now. Materials testing, what is it? So it's a physical test of a material. It's a comparison with either a specification, a standard, or a known reference. And we do it to determine the mechanical properties of the material. We can use it to identify defects or flaws in the material, to determine the quality of the material, if we're receiving this from suppliers, to evaluate it in design. If we're making something from it, we can actually evaluate the properties of it, and the most suitable material for the requirements for the job. Very often you can change materials to enhance the product or save some costs on it. And with mechanical properties of those materials, we're looking at the elastic and inelastic reaction when a force is applied to material. So this is involving the relationship between stresses and strains being built up in that material. Now, traditionally with testing machines, they're looking at things like load versus extension, or force versus movement, and also against time. And we can look at things like maximum force, the distance traveled, the extension, if it broke, when it broke, what the force was and how far it went. But if we need to have larger samples, or we need to look at test piece sizes and stuff like that, we have to start increasing the size of the capacity of the machine to do this, to get similar readings based on the extension. So what we do is we like to start giving the item dimensions, and from this we can then start looking at stress and strain. So adding a dimension to a test specimen enables us to do this. So first of all, back to basics on what is stress. Everybody is probably aware of stress. From a personal point of view, it's your body's reaction to any change requires an alteration or a reaction, and we respond to stressful situations mentally and physically and emotionally, but materials only ever respond from a physical aspect. And we look at this in engineering as an engineering stress. So when we take a body or a specimen that's subjected to an arbitrary loading, applying pressure to it, it undergoes deformation, it bends, it twists, and it generates an internal force within the body of that material to resist this change. And the magnitude of this resisting force is defined as a stress. The unit of stress is sigma, and it is expressed commonly as the force divided by the area. The little table below shows you the most commonly used units of stress. The most commonly used one in materials testing is the MPa, the megapascal. But as you can see, there are lots of different units there, which are all based around the force, kilograms, pounds, divided by cross-sectional area, centimeters, millimeters squared. We've got pounds per square inch there as well. One of the interesting ones for us is if you look at the megapascal, is also direct equivalent to newtons per millimeter squared. So if we know our cross-sectional area of our sample and we're pulling a force on it and measuring in newtons, we can obviously work out our stress. So as we take a sample and we put it into a testing machine and we're pulling it, we could be doing other types of testing on it, but we'll focus on tension testing at the moment. The item is pulled by the machine at one end, it's fixed to the machine at the other, and we generate a stress in the sample, and we calculate this by force divided by the cross-sectional area. I mentioned that there is stress generated with a tension test, but there are different types of stress that we can apply to a sample. We can do this in compression. We can also do the tension test where we're pulling things apart. We can apply a type of stress in a shearing motion where items can slide over one another. We can apply a torsion or twisting motion to it, and also we can apply a flexural motion, be that in bending in 3 points or a 4-point bending. So we're starting to work out now how we can calculate the stress within a sample. The other one that we are looking at is strain. Now, when you again refer to ask people what strain is, people are familiar with the fact that they might pull a muscle or a tendon. You tend to do that when you overstretch it. It gets more physical stress than it can handle. But in engineering, strain is expressed as a ratio of the deformation to the initial dimension of the body or the material in which the force is applied. And in its simplest terms, we apply a force, we get a change in the physical length or the height of the sample, and we look at the ratio of this change over this new change over the original length of the sample. Hence we can develop the strain. So now we have more information on the sample. So we've got the original sample dimensions in its resting state, and we're now going to apply force to it, and we're going to see how the sample changes its shape, either temporarily or permanently. So the first thing we need to do is we need to be consistent with our measurements. If we're going to measure a sample, we need to have an accurate way of measuring it. The more accurate device you can use for measuring the sample dimensions, the better the accuracy of your calculated values, because stress, after all, is a calculated value based on force and dimensions. So we place our item in a materials testing machine, and then we're going to measure strain now. So we're going to see how much this extends by or compresses by. And the simple method to do this is just measure the distance between the groups where your sample's held. Now, this has inherent problems. You're using a flat sample. It's prone to break where you're gripping it because you're applying a pressure to the side of the sample. You don't always know whereabouts it's going to break, but it would tend to break where you grip it. So we need a solution to this, and many of the testing standards apply this solution in the form of a dumbbell, or sometimes people call it a dog bone. Now, the reason we do this to our samples is, firstly, we've got an enlarged shoulder on the sample, and this helps us a lot with the gripping the sample. We've got a larger surface area, we've got plenty of area to grip with the face of the grip. We also, larger area, we introduce more friction into that, which helps slippage. And then in the center, we've got a gauge section. Now, this is the important part of the specimen. This is where we reduce the size to a very accurate dimension. So deformation and failure is located in this region, and we call this region the gauge length. Now, we could just go directly from a shoulder straight to a cut down diameter or a width of sample. But this would tend to break where the change in dimensions happens. So we introduce a radius, and there are some basic fundamentals for designing or making a specimen. So your transition region from your shoulder down to your neck region should be at least as great as the diameter, and your total length of your reduced section should be about 4 times the diameter, the width of the sample. And those are just general rules, but we get these given to us in a lot of the testing standards. And you can see here there's some basic pictures of different types of dumbbells that we can do. There's ones with threaded ends and stuff, there's flat ones, rectangular ones. There are ones taken from pipes, flat sheet ones as well, lots of different types. And the standards give us different sort of recommended methods for gripping it based on experience. And as an example for one of the testing standards for the metals, and you can see here there that you can have a threaded grip You can have serrated wedges to hold a wedge grip, which is going to tighten as the force increases. You can hold the shoulder of it for split collar on round samples, flat samples, serrated wedges, or even a pin grip, which is a vice grip with a pin through to hold it. So there's lots of different types of grips you can use. And part of it for us when we're discussing it with customers, if we've got a known material and known dimension of specimen, then we can recommend the grips. And this tends to be rated on the force of the grip, the maximum force that's going to be occurring during the test, and also the area of the sample that we're going to be gripping, obviously width, thickness, diameter. You can see for things like round samples, we can swap between faces when we need to have a different sample put in there. But lots of different options. So we've done our measurements of our sample dimensions, and now we're going to have to look at the strain. So if we want to measure this change in length, we can't use the machine if we've got a dumbbell, because we're looking at the center gauge length section. So we use what's called an extensometer. So an extensometer is an instrument that measures the test specimen elongation to characterize strain. And the range of applications where extensometer are used is very diverse. And you tend to find there's no real single device that meets all the needs for all the applications. So the requirements for an extensometer are determined by the characteristics of the materials to be tested, its shape, its dimensions, the requirements of the test, and a test standard if you're following one. Here at Mecmesin, we use a company called Epsilon Corp, very well known globally, and they make extensometers, all different types of extensometers. Really one of the most common ones that we use in the materials testing world for tensile testing is an example there, the 3542 extensometer. And these are clip-on extensometers. You physically attach them to the sample. They have a gauge length setting, which is a physical pin setting. The pin's removed before testing, and as the arms open on the extensometer, it measures the change in distance and measures your strain. And you tend to specify these by your initial gauge length, which is fixed, the measuring range, because materials obviously extend by different amounts, and they do this as a percentage of its original gauge length. So you can see on there, you had a 50mm gauge length, you might have up to 100% strain on that, so up to 50mm more movement, and you can mix and match these to suit, and there's obviously other temperature requirements. And they do lots of other different types of axle extensometers. They do miniature ones, they do long gauge length ones, which are suitable for doing wires and thin bar. Heavy duty rebar ones for testing rebar. They can average from two sides. They can do high elongation. They also do lots of other ones which are associated not only with axial, but also they do transverse and averaging and diametrical. A lot of it depends on the test and the sample dimensions and what you're actually looking for. So looking at these materials here, they tend to be low elongating materials. If, however, you're looking for something like an elastomer, a rubber, a very flexible plastic, you tend to be looking for a long travel extensometer. We have 3 models available, varying on different height from 7, 1000, and 1200 millimeters. Looking at these total travel, and these will again clip onto the sample. The advantage of these is you can set variable gauge lengths by changing the gauge length on it, and they have a high elongation to measure strain. Finally, on these, move on to the next level, which is what a lot of people are using these days. The cost can be sometimes prohibitive, dependent on the amount of testing that you're doing, is the video or DIC systems. They're either digital tracking of markers on the sample, so you can actually look at these markers as they move, and also the width of the sample by its image, or you're looking at matching object surface movement during the sample stress. And to be fair, these can get some very good accurate results, and they're very multifunctional. And there are lots of them available on the market. They can either be used as a standalone system, or they can be integrated with equipment for doing the strain measurements with non-contacting. Particularly useful for samples that can get damaged easily by a contacting extensometer. So we'll just look at some of the familiar terms that you'll get within materials testing. Lots of them are all easily, some are calculated, some are inherently properties of materials. But when we start to apply stress, we divide this by the cross-sectional area, and the strain is our change in length. We can start generating data from this. And there you'll see a graph of a material which is started to be pulled in tension, and then finally comes down to a break after 20% strain. So when we're looking at strain and stress, so we look at the definition of stress is the load by the cross-sectional area. Now, when we mean cross-sectional area, that's what we set apart the definitions of what we call true strain versus engineering, true stress versus engineering. The difference being is that if we look at the diagram there, you'll see that as the sample extends, it starts to what we call neck in the middle before it breaks. So it starts to weaken and thin, and that area keeps on decreasing whereas we start to increase the length till it breaks. So this increase in length is compensated by a decrease in the cross-sectional area. And this is a virtue of what we call the Poisson's effect, which is the change in the width over the change in the length. So when you look at it, the initial length or the area that you're referring to is an engineering strain or stress. You would take the current or the instant, then it's a true strain. If it's the dimensions at the beginning of the test and they're kept the same, then it's an engineering strain. Now, materials we're looking at here, the majority of materials have a certain amount of elasticity in them. There's the Hooke's law, scientist Robert Hooke, and it states that for relatively small deformations of an object, displacement or the size of the deformation is directly proportional to the deforming force or load. So under these conditions, an object returns to its normal size when you remove the force. And you can see from the diagram there, if we add mass to the spring, we increase the spring length by X. We double the mass, we double the length of the spring, and so on and so forth. And this will keep increasing until we reach a point where it's no longer elastic. So this area, as we increase, is called the elastic region. And it's very important to look at this for material scientists, the elastic region of a property, because up to that elastic region, the end of that elastic region, removing any force on it will allow the material to return back to its original size. Once we pass this region, we enter the plastic region, we start to have permanent deformation on the sample, which means the sample is getting slightly damaged. We continue past this, and then we obviously can break the sample. So what we look at here is we need to look at this elastic region, and we term this as Young's modulus. So it's a mechanical property that measures the stiffness of a solid material, and it's this relationship between stress and strain in this proportional region of the sample. So the linear elastic region, so where it's going to stretch along this line and come back, when it starts to deviate from it, starts to enter a plastic region. And in software, there's various methods for calculating this. The initial tangent modulus. We can have a secant modulus, which picks the origin and 1 point on the stress strain curve. Or we can pick 2 points for the chord modulus, where we pick 2 defined points, either based on strain or based on stress to get our linear line. So once we start deviating from that line, we do what's called yielding. And it's the point on your stress strain curve that's the limit of this elastic behavior and the beginning of plastic behavior. So yield strength or yield stress is the material property defined as a stress at which the material begins to deform plastically, whereas a yield point is the point where it goes from non-linear elastic to plastic deformation begins. So this is quite important for our material calculations. So what actually happens inside a material? Well, with no load, so your atoms inside your material are sat in a normal state, the specimen has no deformation at all. And then we start to pull on the sample and we start to enter the elastic region. The bonds between the molecules remain intact. Sample begins to elongate and the strain is small. If the force was removed now, the specimen would come back to its original length and they would come back together. But if we keep going, we start to yield on the sample. And you start to see these transition from elastic to plastic. So these atomic bonds have stretched enough to allow the atoms to slip and slide on their planes and over each other. And the specimen stretches and strain increases. If you remove the force now, you have a bit of permanent deformation in the sample. It'll be longer than its original length. We start to approach maximum stress. As we approach maximum stress, they slide and slip and they get rearranged, and the specimen continues to elongate. Once we exceed a maximum stress, then we start to see what we call necking in the sample, where we get a reduction in the diameter. And the necking region exhibits this highest concentration of stress, because now we have that certain version of the same amount of force over a much smaller area, and it's all concentrated there. And then finally, if we carry on doing this, we will break the bonds. As the stress in the necking region increases, it becomes too large, it overcomes the atomic bonds and the sample breaks. So that is the main points of when we're doing a compression test on what you tension test on what you see happening within the sample itself. We've talked about testing standards and things. Just want to show you a video, and it encompasses some doing a testing. We're going to do this on a rubber sample, and it just takes you roughly through the process of what we're looking at with the software and the machine and an extensometer using it. So if we bear with me, let's play this through. So we'll log in onto the software. We've got a D412 test set I've already created here. We've got the name of it, we've got some notes on it, we tell it what specimen type it is and any notes about the test. Got our dumbbell, we have our width and thickness so we can work out our stress. We've got a gauge length, 50 mil. We're using an extensometer, and we're setting up our brake detector on here. And in our operations, now we need to build an operation to move it. So what we do in the software in Vector Pro is it's a drag and drop. So first thing we'll do is we'll tar out our readings, and then we're going to pull to brake. And we choose our speed that we want to go. We'll do 500 mil a minute, and when we've finished, we'll come back to our starting position ready for our next sample. There are some pre-programmed results in there. If you want to add any additional results, you just drag and drop it in and configure that result. So we're putting a max in here. So we'll do tensile strength, nice simple one, and tensile strength will be off the stress axis. So we'll choose that. So that's our result created. And you can see we've got break in there, Young's modulus, offset yields, and so on and so forth. And we'll start the test. I put a little video in there. Now you see we've got a long travel extensometer there, the elongating of the sample. And this will continue to elongate until we hit break. There we go. Go back and look at the sample. And we can also look at our results from our sample and look at the individual results that we generated. We can look at the individual graphs as well where we establish them. We can also send these out. If we wanted to send this to one of our colleagues or whatever, we can send it via, not via email, we can send it via the cloud. So I'm just sending that one to myself. But it sent me an email, and I've got my email link here. And if I click on it, it will take me to that test up on the cloud. There's the basic test parameters there with some of the results that I generated. There's only one sample in this, so statistically I'm not generating a lot of data. And if I go back, I can change and look at which axis I can print on the stress and strain. And then I can look at different parameters. I can switch them on and off. And when I'm happy with my report, I can print my report. I can look at the individual graphs on there. If I want, I can print it. Incidentally, there's a QR code on there that if you scan that, it will actually generate the report for you yourself using the QR code. So that was basically the overview of the materials testing. It's just a short introduction. We didn't really go into any in depth about the technical things, just to give you an overview as what's happening. And if we've got any questions now, we'll take any questions to fill up the remaining time.
Thanks so much, Carl. I just want to give everybody a few minutes to gather their thoughts, and if you want to enter any questions into the chat box, or if you want to raise your hand, I can unmute you to ask your question. I also just wanted to let everybody know that if you're interested, we do have another upcoming webinar on February the 9th. It will help you understand adhesion strength. This webinar will feature live testing and will focus on 180-degree peel testing, which is one of the most common approaches to measuring the adhesion or bonding strength of adhesives. So if you're interested in that, I will pop a link into the chat box for you to be able to register. So I'm just going to pop on over and see if we've had any questions come in. Great. I see there are a few questions. The first is, are the ASTM and ISO standards the same?
Similar won't be the answer to that. Yeah, the different standard bodies, ASTM, the American standard bodies, and the ISO tends to be focused around the European standards, incorporating standards from different regions like Germany, the British standards, the French standards and things. So they are always reasonably quite similar, but you cannot just say they are exactly alike. And if I test one standard, then it will naturally follow the other standard. There are some differences in the calculations, not the methods of calculations, just the amount of calculations required and results. There are slight changes in testing speeds and things, but what we're seeing over the years is there is an alignment between the testing standards, and they start to, as they redo them, they do start to become very, very similar. But don't take one as read that it's exactly the same from an ASTM to an ISO to a JIS standard. It will be slightly different. So you're always better off acquiring the standard and then reading through it before you do your test. Okay.
Thanks, Carl. And there's another one. Can you do high elastic samples with video extensometers?
Yeah, yeah, the ones that we looked at there. The problem, well, not a problem you have, is with video extensometry, it's optical based. And with any optical system, you have a lens. And if any of you do photography, you'll know you have what's called your field of view. So you think about it, if you're up close with your camera, you can see a certain amount of the sample. You move further away, you see more of the sample. But the further you move away, the less your resolution becomes. So to get over this, what they do with a lot of camera systems is a single camera system will have a defined field of view, and it will give the different accuracies at distances away for fields of view. But then you reach the sort of the limitations of the lens and lens correction. So what they do is they double up with the camera lenses. So you have an overlap. So if you had a high elongating sample, you may have 2, possibly even 3 camera lenses that have an overlap between each one. And then within the software, it picks up the movement as it tracks between the lenses to give you a high elongating sample. Okay.
Thank you. And one of the other questions that came in, is it possible to extract the raw data into an Excel spreadsheet, for example?
Yes. Once the equipment streams 5 channels of data at any one point. So we send out time, load, and displacement, but we also send out stress and strain. Now, the stress and strain is a calculated value, but we're not actually calculating it in the software. We're getting the machine to do the calculations on it, because what we do is we're loading the specimen dimensions and the gauge length and things into the machine software. So the machine software is doing this on the fly, because it knows what its load is, its displacement, its extensometer movement. And we stream that from the machine, and because we do that, that's how we produce the graphs in the system. And from that, the calculated results are displayed. Because it's data like that, yes, we can export it. We can put it out as a CSV file. We can do it as a comma separated. We can do it as a text file. We can do it to Excel. Obviously, Excel has limitations on how much you can display if you're doing a very long, high frequency, high sampling rate test. You have to be wary of the limitations. So not only is it just the individual results we can kick out, we can also throw out the data as well. So you'll get 5 columns of data with a timestamp based, and then load, displacement, stress and strain. And then you can do what you want from that in Excel or any other programs that you've got if you want to generate your own results. Okay.
Great. We've got another question. Is the elongation measured by the video extensometers integrated in the VectorPro software?
At the moment, we've experimented with 2 different types, a DIC and a standard video extensometer. We have been able to integrate these into the machine. It can be run as standalone systems, but we can at the moment, we are just still finalizing some work with that to integrate them directly into the system. We have different ways that we can do this. We can either treat it as a standard extensometer, where we'll feed the output of it into the extensometer socket, as we would when you saw the Epsilon or the long travel extensometers, and just treat it like an ordinary extensometer, because these systems have analog outputs. We've done that at the moment, and that's reasonably adequate. What we'd like to do in the future is to integrate it from a digital point of view. So rather than have that changing between a digital signal back to an analog signal, back to a digital signal, we take the pure digital signals in. So at the moment, yes, we can integrate those into the systems, and it will be on a case-by-case basis as well, on what system is required based on the samples itself. And then hopefully in the future we'll have APIs which we can integrate directly with the software rather than the machine and stuff to do that. Okay.
Thank you so much, Carl. I don't see any more questions. So for now, I think we'll turn off the chat box. If there are any follow-up questions you'd like to have answered, please send them for my attention at the email as it's shown on the screen currently. Again, thank you so much for joining us today. We look forward to hosting you some other time, and we hope that you enjoy the rest of your day.